And the last lecture will be given by Suvrat, and invite him to do so.
So thank you. I know all of you are very tired, so I'll try and make this as exciting as I can. I'm going to basically, try and tell you today why all the paradoxes I told you about yesterday, all these Mathur MPS paradoxes are actually moot, and that there's no firewall. So I'm going to try and show you how you can construct these operators O tilde so that there's no firewall. Okay, so that's basically the plan of the talk. Remember in the past two lectures, I spent a lot of time trying to describe how the issue of whether or not you had a smooth horizon was related to the issue of whether or not these operators O tilde could be defined in the theory. And today I'm going to try and define them and hence argue that there's no firewall, and also resolve all the different paradoxes of Mathur and MPS. Okay. Okay. So before we construct these operators, it's useful to have a sense what are the possible observables you can really measure in the CFT. Okay? So when you talk about the CFT and when you talk about local physics and local space-time physics, there may be various bounds on local space-time physics, but it's certainly true that if you start measuring very fine correlation functions in the CFT, forget about constructing local operators. There's not even necessarily a smooth space-time semi-classical bulk description that can reproduce for you these very fine correlation functions. Okay, so the first thing to realize is that the bulk space-time description can't give you infinite accuracy. Okay, so it can give you accuracy up to some point, but eventually, if you start asking very, very careful questions in the CFT, then you need to be careful about non-perturbative effects, and you need to be careful about many different things, and so you need to limit your resolution in the CFT. Now, I'm not going to limit my resolution too much, but I'm going to do the following things. So far, I've talked about the CFT on the plane just for simplicity, but I'll say I'll put the CFT on a sphere. That's actually a good thing to do because it makes everything well defined. So on a sphere. Okay, so if you're working with n equal to 4 superangles, I'll put the CFT on S3. Okay, and second, I'm going to put the CFT on some kind of lattice on the boundary. Okay, more precisely, what I'm going to say is that you have these observables O. Okay, these operators O. Actually, O could, as I said, be any of many different types of observables, and it has some spherical harmonic which is M. Right, this M is related to the sphere. Okay. And I'm going to say then there are some additional frequencies that you can measure, and those frequencies I'm going to denote by omega n. Okay. Now, omega n is something that I'm happy to all I want is to discretize the observables I have. And omega n, if you like, can even be equal to m into e to the minus n. Okay, where the n equal to 4 superangles theory. So this is something which could be a very fine frequency. Okay. So you certainly can't measure things to accuracy larger than e to the minus n. This is like saying you put a lattice on the boundary and you put e to the n points on the boundary, okay, which is certainly more than anything you might need for any real question you might ask. Okay. So more precisely, this is equal to m into omega IR, and omega IR may even be e to the minus n in n equal to 4 SUN theory. Okay, so omega IR can be very small. Okay, it can be a discretization, but it's bounded. Okay, and it's bound. This bound is not important for anything except I need to work with discrete things. Okay, this is the first limitation. The second limitation is what you can really measure are some correlation functions. Okay, but you can't measure again arbitrarily high correlation functions and expect to get a good smooth space-time description. Okay, so we can discuss this later in more detail if you like. But I'm going to allow you to measure correlation functions of these operators, okay, omega k and k, okay, in the state psi, whatever the state psi is, okay. And I'm going to put two restrictions on these correlation functions. I'm going to say that the highest point correlator you can measure is limited by some k smaller than equal to some capital K, which is much smaller than n squared. Okay. Now, when I say n squared, I'm referring to the SUN theory. Actually, if you look at our paper, we use curly n, and where curly n refers to the central charge, which is the same as n squared here. So, if you happen to look at this paper we wrote with Kyriakos, in which I discussed a lot of this, you'll see that n squared, wherever I write n squared here, you should translate to curly n there, which is the central charge. Okay. So there's a limit on the maximum number of insertions you can put in a correlator, and that's also a very reasonable limit, because if you start measuring correlators with n squared insertions, then you certainly shouldn't expect that those correlators necessarily have a smooth bulk interpretation. Okay, in any case, I'm going to make this limitation, and there's another limitation you should put, which is that the sum of the energies, okay, is also smaller than n squared, and the reason for that is simply that if you have insertions, if you have so many insertions that the insertions themselves can create a black hole, then again you don't expect to have a good semi-classical description of that correlation function. Okay, so the important thing is that I'm going to limit the observables I have. The first thing I've done is I've discretized the frequencies, and this is not very important, but I have discretized them. And second, I said you can measure correlators with a finite number of insertions and an energy, both of which is smaller than n squared. Okay, and these are reasonable restrictions. They certainly cover most perturbative observables of interest that we might care to look at. And in fact, they're kind of fundamental from a space-time point of view, in that if you want any sense of a semi-classical space-time to exist, you should put these restrictions on CFT correlation functions. And if you start measuring more general CFT correlators, then it's not at all clear that the bulk has there's some saddle point approximation that captures the dual of these CFT correlators. Okay, so is this clear? This, if you measure a correlator of this kind, then on this correlator there are two restrictions. One of them is that this k, the number of insertions you have, is much smaller than n squared. Second, the total energy of the insertions, by summing up all the energies, is also much smaller than n squared. There are two restrictions on the correlators. Yeah. No, the field theory makes sense, and this, but you don't expect necessarily have a simple dual bulk interpretation, which comes from one saddle point. You don't know what the bulk will be. It might be a sum of different saddle points. You may not have a geometry. There's some very highly quantum gravity regime. So, yeah. No, n squared. It shouldn't be as big as a black hole. I'm happy to allow giant graviton operators. Yeah, but I'm happy to allow. Yeah, okay. You can think of some operators that are. Yeah, I think. I mean, that's not a constraint for the construction I'm going to do today. It's certainly a constraint for all the construction, for this explicit construction of bulk fields and so on that I talked about yesterday. Where if yesterday and the day before that, where you try and construct a bulk local observable. Certainly, if you had a giant graviton, you might want to be, you might want to do that in a more careful. But for the construction I'm going to describe today, it's actually a much. The reason I'm putting this restriction is that this construction of mirror operators or tilde operators I'm going to describe today is something that works in a pretty general statistical mechanics sense, and it'll work as long as I restrict my correlators and observables to this. So I am allowed to insert giant gravitons and stringy probes, and that's not a problem for the construction I'll do today. For the formulas I wrote down yesterday and the day before that, you could ask if you're allowed to do that. Perhaps the things you're talking about also these dual giant gravitons. Yeah, you might worry about them, but yeah, strap around. But not for what I'm doing today. For the formulas yesterday and before that, yeah. Okay, is this restriction here? Yeah.
What is the notation k? I'll understand less than. What is that notation k less than?
Small k is less than k, which is less than n squared. So small k is just a number. Let me use p here to avoid getting. So I'm just saying you can measure all correlators up to some limit, which I put ahead of time, which is much smaller than n squared. So you don't, I put a limit at, let's say, n or n squared by 100, and you can measure all correlators up from 2-point functions to n squared by 100. Okay, but that's a limit. Okay. For some things like the spin chain and so on, I'll talk about. I can put a much sharper limit, which we can discuss if we have time in the end, or maybe in the discussion session. Okay. Okay. Good. Now. Let me try and formalize this a little more. Okay, so let me say that instead of considering so if you think of all such operators that you have, you can actually you can equivalently think of the set of all polynomials, okay, in CFT modes, which I'll call alpha, which go over alpha into nm over omega n, and so maybe I should put one more number, nm into p omega n m raised to the power p. Okay, so you can think of some let's see, what notation should I use? sorry, I'm just trying to get the notation right. Let's take a product in, and sorry. I'm just trying to write down polynomials and trying to make it more formal. P n m product over n m alpha n m p. Okay. Sorry, this is unnecessarily formal. All I'm saying is that you consider some polynomials in these modes. Okay, so this is a polynomial in these modes. You can also take linear combinations of these polynomials. Okay, so you take each mode O n m, you raise it to some power p n m. Okay, you multiply over all possible modes. For some of these modes, remember p has to be 0 by a bound in energy and by the total number of insertions that we have. And then you take linear combinations of many such products, which is arranged by this alpha. Okay, and so you take a linear combination over such products, and that gives you some polynomial. Okay. So this A alpha is just simply some polynomial. Okay, it's some polynomial in the in these modes O alpha m, and in the polynomial is such that each monomial satisfies this constraint. Okay, so I'm sorry for the excessively formal notation, but I hope what this A alpha is clear. Okay, is this A alpha clear? Or is this notation confusing? Okay, so A alpha is a polynomial in these modes where each monomial satisfies this condition. Okay, fine. Now let me take a state psi.
P a function of nm or not?
P is a function of nm, and actually alpha should be maybe only a function of p of nm, and then you sum over p. First you give me p as a function of nm. That describes for you a monomial, where you take a product over all nm and O omega n raised to the power p and nm. Okay, then you sum over all possible p's that you might have with some linear function. Okay, which is alpha, and then you sum over. Okay, so with some coefficient. Okay, this is unnecessarily formal. Okay, it's just a polynomial. Okay, fine. Now you take some state psi. Okay, take a state psi, okay, and consider the following Hilbert space, the following linear space, which I call H psi, which is given by taking all possible polynomials of this kind and acting them on the state psi. Okay, so I take all possible polynomials of this kind and I act them on the state psi. Okay, so if you like, I can write the span of A alpha psi. Okay, so this is a linear vector space because the polynomials are a linear space. Okay, so this is the space H psi, which is given by taking your pure state psi. Psi is some is a highly energetic state dual to a black hole. Energetic state with energy larger than n squared, not parametrically larger, but larger than n squared that you're above the Hawking page transition bound. Okay, and then you consider this space H psi. Okay, now there's an important question here, an important point here which I want to make, which is that you can count the dimensions of this space H psi. Okay, or you can count how many linearly independent polynomials do you have. Okay, with the restriction of course that that sum of p and m is smaller than this k that I defined there. Okay, and also that the sum of omega n into p and m, okay, is smaller than n squared. Okay, so you have these two restrictions on each monomial. Okay, and you can ask how many different polynomials do you have in the mode with these two different restrictions. Okay, now we don't want to do a very accurate counting because the accurate counting depends also on an index that I've suppressed here, which is how many different kinds of modes are you looking at. Okay, so you might have here trace of f square, or you might have the stress tensor, and you might have different flavors of these fields that you're considering, and so an accurate counting depends on that. It also depends on how precisely you discretize and at how many n's do you have, okay, whether you put the discretum at e to the minus n or at some other number. Okay, but the fact is that if you count this number, whatever it is, okay, and I define this as dA, which is also the dimension of H psi, okay, this is smaller than e to the n squared by these conditions. And the reason it's smaller than e to the n squared is that the total number of modes you have here, let's say these are e to the n modes. Okay, so let's say you have e to the n different frequencies you can insert, okay, and you can insert at most up to k of them. Okay, so the number of ways you can insert them is e to the kn. If k is much smaller than n squared, then this is also much smaller than e to the n squared. Okay, maybe you want to put uh, actually maybe I should. So there's an interplay also between how exactly you put this bound and how exactly you put k. Okay, but provided you keep all of these things small, okay, provided you keep all of these things much smaller than n squared, you'll see that the dimension of the polynomials you get is much smaller than e to the n squared. Okay, is this counting argument clear? As I said, there are three things that go into the counting. There's how accurately you discretize. Okay, there's what bound you put in k and what bound you put in the energy. Okay, but you can keep all of these large. You can keep a pretty fine discretization. You can allow many high insertions, and you can allow energies that also scale with n. Okay, and you can still make sure that the number of independent polynomials you get is smaller than e to the n squared. Okay, this is the same as this constraint. Okay, is smaller than or equal to k, which is where k is much smaller than n squared. Well, so there's one more parameter here, which is how many different frequencies do you have, which depends on this. Okay, how you put this cutoff. Okay. So if you put this cutoff to be 1 by n, which is actually a pretty good cutoff, so that you're looking at frequencies only at 1 by n, then you are allowed a larger k. If you put this cutoff very high, if you put this cutoff at e to the minus n, then in fact you have to take k to be smaller than n. Okay, so you can't measure more than n point correlators. So the total number of insertions doesn't go like e to the n squared. Okay, so there's a, and it also depends on how many different flavors you have. Okay, but the fact is that if you provided you juggle these things appropriately, you can get all kinds of correlators of interest, very high point correlators, very fine frequencies, and energies that are reasonably high, and still keep the total number of observables less than n squared. It's I beg your pardon. It's what?
When you say flavors, you don't mean just the few fields that are there in your theory.
Indeed, but once you start taking, that's right. But once you start taking some number of low single trace operators, and you're allowed to take arbitrary products of them, that presumably also generates a lot of higher higher gauge invariant operators. For example, there are double trace operators of trace of f square of the stress tensor, but rather than considering the double trace operators separately, I might just as well consider products of the stress tensor. So you could consider trace of phi to the n, sure. I mean, and you're allowed to consider those guys also. There would be a Hagedorn density of those states. Yeah, there would be a Hagedorn density because there's some string theory growth of those states. Yes, yes. I mean, all I'm saying is the total number of. Sorry, yeah. I mean you can partition it amongst bins, yes, but remember I'm also allowing you to take only up to products of k of these guys. There are many different flavors, but those flavors also have higher and higher energy. So for example, there may be giant graviton operators, but they have higher energy, and then you have to partition things. But remember also that one restriction in your partitioning is that you can't take a very low energy operator and insert it n squared times. Now that's what gives you large numbers in this partition. So if for example it's a partition into k parts, exactly. It's a partition into k parts. So you have some spectrum of some energies, and you have to partition it into k parts. And if I keep k much smaller than n squared, then you can count these polynomials, and they're much smaller than e to the n squared. You can work out the exact bound depending on how you put the IR cutoff and how you put these things. But it's not a restrictive bound. So that's just products of these guys, you mean? Multi-particles of these guys? Yes.
That's much less in number compared to the number of single string excitations that you'll get. Because the number of
Okay, you know, already if you actually count number of, so you know, this bound on omega is actually important, because for example, if you put this bound, you know, if you look at, if you just think of a scalar field that's living outside, and you know, you put a bound at 1 by n to some power, 1 by n cube, or you know, 1 by n cube, and then you consider all possible ways in which you can partition an energy of n squared in frequencies that are bounded by 1 by n cube, you will in fact already get the black hole entropy. You know, and the reason for that is that, you know, there's no gap here. You can have some very low energy modes that will already count for you the black hole entropy, but that will violate this k bound. So I mean, but I'm happy to allow you to include, you know, all sorts of string states. So you know, you have these graviton states which have some this thing, and then you can take n of them and get, you know, some determinant states and so on, and I'm happy to let you do that. I'm just saying that the total number of operators that you will count in this way, which have, you know, which have dimension much less than e to the which have dimension much less than n square, is much smaller than the total number of microstates that you have. All I'm saying is I'm restricting you so that you can't by one measurement of an operator tell me which microstate you're in. I'm letting you measure many possible operators, but not e to the n square operators, which is a reasonable restriction. Okay, so that's a restriction. Now there's something very important that happens. You know, there are psi. You know, if I pick psi of, you know, generic states with energy E much larger than n squared, okay, then you know, this condition that dA is much smaller than e to the n squared implies that for a generic state psi, for all alpha, for all polynomials, okay, and that's simply the statement that if I give you a set, you know, some linear operators which has a dimension smaller than the dimension of the vector space, then none of those operators annihilates a generic vector in the vector space. Okay. In fact, the set of vectors that are annihilated by one of these polynomials are a set of measure 0. So it's not only that they're exponentially suppressed, they're really a set of measure 0. Okay. So if I give you, you know, if I give you a 10-dimensional vector space and I give you 5 operators and I ask you, you know, pick a generic vector in the 10-dimensional vector space, what is the probability of one of these 5 operators annihilates this vector? The probability is 0. It's really a measure 0 set. Okay, so the fact that dA is much smaller than n squared implies also that A alpha psi is not equal to 0 for any alpha, except of course if A alpha is identically 0, and then it's 0. Okay, so this is important. So these are linearly, you know, the states that you get, the vector states that you get, if I call these guys V alpha is equal to A alpha psi. Okay, these vectors also span a Hilbert space, which is really, you know, so the dimension of this space of polynomials is the space is the same as the dimension of H psi. Okay. Now,
let me just make sure. H of psi is the set of all operators which can be written.
so H of psi is the span of E alpha acting on psi.
Span means what? Set of all
Means
operators.
I take all the polynomials, I act them on the state psi,
State psi.
I get many different vectors, and I consider the vector space formed by taking all possible linear combinations of these.
That's what I thought. Okay. So that is H of psi.
That's it. So I shouldn't have written this. I argued for this equality there. Yes, dA is a set. So let me call dA. Let me call dA equal to dim of A alpha. Okay, the set A alpha, the set of all polynomials. Okay. And so then the question is dA equal to dim of H of psi? And is the dimension of the set of all polynomials equal to the dimension of the Hilbert space I get in this way? Those two would not have been equal if any of the polynomials I had annihilated the state psi. But I am arguing that for the generic state, in fact for all but a measure 0 set of states, the polynomials don't annihilate the state psi. And so dimension of H of psi is the same as dim dA, as the set of dimension of operators.
So I've asked you this before, but that's about. I mean, this for a black hole which is excited just somewhat above extremality, this would not be true, right? And now you're saying that it's you can excite it up to energy n above extremality, which is of course much smaller than n square.
So you're worried about black holes excited above extremality because some charge can annihilate it?
Yeah.
Because some number of so you know let me for a minute,
but
you know,
I don't mean now the global charges. I mean now some I mean I don't mean some conserved charges. It's just when something is above extremality, you just descend further. I mean, just
So
go down.
you know, you're saying that you can excite by acting with enough number of E minus Qs. So the statement is that, you know, it lives in a small representation of the charge. You know, you can think of this as living in a small representation of the charge. That's really the statement, right? And that's why, you know, the highest charge that you have here is bounded by some amount, and so you can kill it by acting with some number of lowering operators.
Not I mean, charge might be, I mean, at the extremal, so it's the charge is equal to the mass or whatever, which is large.
And then you excite it a
and
little
then
bit.
you excite it by some amount above that.
Right, and so okay, okay, you can do that. You can, um, you know
Near extreme,
right,
not infinitesimally near extreme.
right. You know, the thing with extremal black holes, things that are very close to extremal black holes is that a lot of, you know, what I said yesterday breaks down, because also the entanglement between these two things, which goes like e to the minus, you know, the entanglement is also controlled by some e to the beta, and that entanglement is also not required, you know, because beta goes to infinity. So, you know, you also don't need to have very strong entanglement between things on the left and on the right. So what I'm trying to do here, you know, trying to construct these O tilde operators, this is something that's a good thing to consider if you have, you know, a black hole sitting in AdS. We have some finite temperature, and then if you're going to take a temperature that's parametrically small, then indeed this construction will break down. In fact, it will break down for an extremal. You could think of an extremal black hole, in which case, you know, you might.
Extremal is this thing, but
Yep.
here it's an energy. Okay, I agree that it's near in the sense that it's parametrically small because the energy is only n, the exciting.
So the temperature is 1 by n or something. So that's right. The temperature is 1 by n, and indeed I think it will be true that, you know, in some you will not be able to construct all the mirror operators, but that's also okay, because I think, you know, in the end you don't need also these mirror operators. You don't need this entanglement, because entanglement. Can I write down a few formulas and we can discuss the beta goes to infinity limit in the end? It's a slightly extreme case. Let me just write down some of these formulas. I think you can also see that in the limit where you go towards extremality, these mirror operators also, you know, kind of start going to zero almost. They start acting as if they just annihilate the state. So that's actually consistent. If you can just ask me the question in the end about extremality. Although extremality I think needs to be, you know, explored a little more, but if you could just in the end about. So for now, let's just consider a big black hole in AdS. You can put some charge in it, but let me just consider a big black hole that's far away from extremality, so it has finite temperature. It has some temperature that's order 1. Okay? Okay, good. Now I'm going to define for you the mirror operators. Okay? The definition of the mirror operators is as follows. It's very simple. So O tilde, okay, of omega n and m. Remember, this is the O tilde operator that I discussed, you know, ad infinitum in the past 2 lectures. Acting on any of these states, on any state in H psi, is defined as follows. Okay, that's it. Okay, that's the definition of O tilde. Now, what do I mean by this really? What I mean by this really is I want to find an operator, okay, in this space, so that it satisfies this set of linear equations. Okay, so that for any vector A alpha, you know, any polynomial A alpha, when I act it on psi, the action of O tilde on this vector that's produced by A alpha acting on psi is the same as this thing on the right hand side. Okay. Now you could ask, how do you know that you can find a solution to something like this? The reason I know you can find a solution to something like this is that if I can satisfy this equation for any basis in A alpha psi, or just for a basis of vectors in A alpha psi, then I know I have satisfied this equation for all polynomials, A alpha. And the reason these linear equations are consistent for any basis is that, you know, by this condition, by this very important condition, okay, vectors in the basis are linearly independent. It is always possible to specify the action of a linear operator on any given set of linearly independent vectors. Okay. You give me a set of linearly independent vectors, and you give me a linear operator, and you tell me anything on the right hand side, and I'll find a linear operator that satisfies this, that has this behavior. So it's always possible to specify the action of a linear operator on a set of linearly independent vectors, and by this condition, this very important no annihilation condition, which came from counting, okay, you can find a solution to these equations. Okay, if I have time at the end, or if I have, in the discussion session, if you ask separately, I'll show you how you can solve this in various toy models. So if you can take a spin chain toy model and solve these linear equations and get these operators concretely. But you shouldn't be really worried about the existence of them, because I just argued for you that these linear equations have a solution. So this gives you a set of linear equations for for these O tilde operators, and I'm claiming this is a proof that they have a solution. Okay, the proof is simply that A alpha psi is not equal to 0, and I can specify the action of O tilde on any set of linearly independent vectors. I can always find a solution. Okay, and of course, if you're not happy with that, I will show you in toy models that it can be done, and maybe at the end of this lecture if I have time. Yeah.
So V alpha is what is your DA? I mean the set of V alpha will be.
Yeah, just A alpha. Yeah, I'm not going to use V alpha here.
So suppose suppose I want to find out D of say DA of V alpha. Is it allowed or not?
DA of, sorry, what does DA of V alpha mean? DA is just a dimension of H psi.
Yeah. So
H psi is spanned by all possible V alphas.
yeah. So I'm saying suppose I want to act on A alpha on V alpha.
With another A alpha and V alpha, it is allowed as long as the product of the polynomial still lives in your set of allowed polynomials. Now, A alpha is a polynomial. So you can act with one polynomial and act again with another polynomial. The polynomials are a ring, so product of polynomials is another polynomial. But you have to be careful that your new polynomial also satisfies the constraints I wrote, these constraints. So you can take products of polynomials, but the product better satisfy this constraint. It shouldn't take you out of the set. It's a slightly restricted ring. It's a ring where you can take products of some elements, but not of all elements. If you take too many products of A alpha, then you have too many insertions. Then you go outside this set.
So the way I want to think that I want to start with V alpha as a new state. So I'll act on.
Yeah, let me write this in the following. This is okay. Whatever this omega n was. Okay. So it's this A alpha is really just some product of things like this. It's nothing mysterious. It's just a product of some O's. You can of course multiply two A alphas. You'll get a product of more O's. But you can't have a product of too many O's. You can't take a product of more than k O's. So you can if I give you a product of 2 O's, another product of 3 O's, you can multiply them, you'll get a product of 5 O's. But you can't keep doing it, because in the end you cross this limit I set.
What I don't understand, what is the special about psi? I mean, V alpha is another state, right? Some other state.
Yes.
So I could have started from V alpha.
Yes, I'll talk about that in the end. So psi is right now a generic black hole state. Let me talk about what you're asking later in the end. So psi is the initial black hole state. So you give me a black hole state which is formed from collapse. I wait for some time. I start with some generic state, or I wait for some time. I let it equilibrate. This is my state psi. Okay, I'll start with psi. Now the question of whether you could have started with V alpha, I'll come to later at the end. Okay, so psi is your black hole state. V alpha is not your black hole state. V alpha is a black hole state plus some excitations on top of it, which you've created by acting with omega. So it looks different from the black hole state. Yeah. Which would be A alpha psi. Yeah. Or a basis of A alpha psi. Yeah. So you can arbitrarily specify the action of any linear operator on a set of linearly independent vectors. So this is the right hand side for the linear equations. So I'm telling you the action of O tilde on a set of linearly independent vectors. This is the right hand side. So O tilde acting on linearly independent vector gives you take one element V alpha basis, it gives you this. Take another element, it gives you the right hand side. Take a third element, it gives you something else. So you can this is the right hand side of the vectors. That's what I meant by saying that you can arbitrarily specify the action of O tilde on any set of independent vectors, and this is the specification. The right hand side gives you the specification. Okay, so this is the specification. No, is an operator I want to find. I'm finding it by solving these linear equations. Okay. Yeah.
Odagas are already known, right?
Odagas is already known. Odagas is just already known. Yeah.
Right hand side, I expected O dagger to have something acting on A alpha side because that's your state. Why is it?
No, it's not acting on A alpha side. This is the definition. It crosses through. This is how I define my O tildes. Okay, the O tilde doesn't turn into an O dagger. It crosses A alpha and then turns into an O dagger. I'm free to make that definition, right? We'll see it has all the right properties.
Are you putting any constraints out of this subspace aside from?
No. Outside this subspace, the action of O tilde is not specified. We'll see it's not important within if I restrict myself to correlators of this kind.
Important for this.
For this, and beyond that, I'm not putting any constraint.
But you, in some ultimate sense, you will have to specify them.
In some ultimate sense, I'll have to specify it. It's true. Let me take it right now to act as 0 outside the subspace. It's a little bit like saying that, you give me a field operator and I solve it in perturbation theory. You haven't entirely specified the action. It's true. The action of O alpha outside this subspace is a question of very accurately, in some sense, specifying O tilde. I don't have any natural way to make that very accurate specification. So let me take it to be 0 and it won't affect any low point correlators.
You want some notions of continuity and so on, and I mean.
Yeah, we could impose that. You could impose a notion of continuity. There are many ways to do it, but there's nothing which is particularly natural.
No, I agree that, but in fact, that's what worries me. I think that, that aside from this definition, there is nothing that characterizes O tilde.
In some sense, O tildes are operators you want in effective field theory. So, what you want is that they should act correctly within low point correlators. But you don't know the exact operators, but that's true. You don't know the exact operators. There are many other there are other natural definitions you could take, which we can try and discuss. For example, you could try and say that you define it for one psi and some other psi which is very far away in the Hilbert space, and then you try and make them work. And there are many such things you can do. So we can do that, but none of those is necessarily immediately very natural. But you could try and make it so that things are continuous or whatever as you change psi. You could try and do that. You could try and yes. Maybe, but this is a property of this is a very fine property of the O tildes. It's a property of O tildes that only appears when you look at very, very high point correlators. I don't know how to specify it in some natural way. That's something that needs maybe further investigation. It's a little bit like saying, can you specify for me what is the graviton field that I had in the bulk? And somebody else can do a field redefinition. So the graviton field changes at some very high order in the 1 over n expansion. And my operator is different from your operator. And but I don't know. I know how to specify the graviton field in some perturbative expansion as some operator plus some 1 over n corrections. But I don't know how to calculate the very high order corrections. I think this issue of how it acts outside A alpha psi is an issue of how it behaves inside very high point correlators. So it's in some sense it's a question of some very high order corrections to O alpha, because it matters only when you look at correlation functions that are non-perturbatively suppressed, that are very high order in 1 over n. Why not what?
Acting on the vacuum.
Or A alpha acting in the vacuum. That's not specified. I don't know how to specify that.
It's not specified, but shouldn't that be that?
So the mirror modes don't in some sense exist if you have just the vacuum. You shouldn't be able to define the mirror operators in the vacuum. If you just have the vacuum and you have you don't have a black hole, these interior operators don't exist. So it's not clear why we should have to specify O tilde acting.
I mean, that is, so now you're bringing it up. That's what I mean is that if O tilde is an operator, so are you saying that O tilde is 0 when acting on?
Let me specify O tilde to be 0 outside the sub. That's my definition. Okay, so let me give you a concrete definition. O tilde acting on V where is equal to 0 if V is orthogonal to H psi. Okay, this is my definition. So that completes it, if you like. This is not a particularly natural definition, but if you push me in it, I'll make this definition. Yeah. No, the proof will go through. Everything will go through. This will completely not affect anything. Yeah. Okay. This may be a slightly subtle issue, so we can talk.
Just to make a comment. I mean, did I understand Ashok's comment right? Is he here? Oh yeah. Ashok's comment right? That you were thinking that you should be able to propagate the modes back and therefore define it. But even if you did it like that, it will depend on the state psi. No?
Yeah. So what I was saying is for a given psi, there should be some specific
Yes.
Okay,
That sounds right.
there may be a
That sounds
natural way to
absolutely right.
specify it. I don't know how to specify it naturally right now, and it won't be important for this thing. It's an interesting question how to specify O alpha on the full space outside its side, but it's not important for the restricted set of correlation functions I have right now. So,
So what he says must be true.
okay, yeah. So there must be a natural way which I'd like to understand, but it's not important for anything we're saying today. Okay. So anyway, now let me say one more thing. I'm probably doing badly for technical. What's the time?
It's 4:17. So
That means what? It's been 40 minutes already?
yeah.
Okay.
What we can do is
Let me take half an hour more. So that will be till 4:40. That will be my 15 minutes extra, and then we'll end. I'll end in half an hour. I'm going to restrict questions, especially the questions which are slightly advanced questions. So which I'm very happy to discuss. But let me just do this. Okay. Let me say one more thing. You know, there's another way of defining these operators, which is to introduce the following map. Okay. This is an antilinear map. Okay. And it's a map from edge side to edge side. Okay, so this is a map from edge side to edge side. Okay. It's an antilinear map, and it has the following action. Acting on A alpha side, it's an A alpha dagger inside. Okay, so it has the following action on polynomials. Okay. This map is actually something that appears in what's called the Tomita-Takesaki theory of modular of Saki theory of automorphisms of von Neumann algebras. Okay. So if you read up something called the Tomita-Takesaki theory, which people who do mathematical quantum field theory are very interested in, it tells you something about automorphisms of von Neumann algebras. Then this map S alpha, this map S, which takes in an operator to its adjoint, this adjoint map also appears there. Okay. Okay. Now this definition I wrote can equivalently be written as O tilde, or actually let me now define more generally the tilde of any operator. In fact, A tilde, A alpha tilde is equal to S to e to the minus beta h, where h is the CFT Hamiltonian. Okay. A alpha e to the beta h by 2 into S. Okay. This is an operator relation that defines the tilde, the mirror or the tilde for any polynomial, including in particular when the polynomial is just something as simple as O. Okay. So you take S, you act on it, you multiply it with S. S is an antilinear operator, and you do this math, and this gives you, A, the mirror effect. Okay. So this is, now you can check that with this definition, if I apply this definition to this case, there are two A alphas. Okay. Here I looked at the mirror of A alpha tilde, and here A alpha is something else that was acting on the state. Okay, but if you apply this definition by putting A alpha and that just to be O, you will find that this equation holds. Okay. So this is completely equivalent to this. Okay, these two are completely equivalent, but this is of some interest because it appears in the mathematical quantum field theory. I just wanted to mention this. I won't say too much more about this Tomita-Takesaki theory. Okay. Now the claim is that first this gives you a smooth horizon. These operators O satisfy this equation that we wrote down yesterday, this fundamental equation we wrote down yesterday, and they resolve all the AMPS parameters. Okay. So the claim is that one claim is that they satisfy conditions for a smooth horizon. And B, they resolve all the AMPS parameters. Okay. So this is the claim. I'm going to now justify both of these claims. The first claim, I spent a couple of lectures trying to describe what was the condition for a smooth horizon. Let me remind you what the condition was. The condition was as follows. Okay, that psi, acting on some, with some O omega 1, something O omega p, some O tilde omega 1. Let me put a finite number of O's just to make this work here. Okay. So the condition was that 1, O tilde omega 1 O tilde omega 2, okay, up to some O of omega p, okay, on psi was just the same as, e to the minus beta into, this is omega sub 2 omega, so this omega 2, omega 3 and omega minus omega 2 plus omega 3 plus all the omegas that appeared with the tildes, okay, into the same psi, and okay, I'm going to remove the dot dot dots just because I want to demonstrate this clearly, and I'm going to cut this p and I'm going to say write this condition just for 4 operators. Okay, so for 4 operators, the condition we wrote, which you can write of course for p operators. So let's say you take the following 4-point function: omega 1, omega 2, omega 3, and omega 4. 2 of these guys are ordinary operators. 2 of these guys are mirror operators. The claim is that this looks like omega 1 into omega 4 into O omega 2 and O omega 3. Okay. And there was a further condition which was that correlators in this look like correlators in the thermal state, but that's a separate condition. The condition we demanded from the O tildes was that that first they should commute to the right of the O's, okay, and second that their operator should be reversed, their ordering should be reversed, okay, and you should get these e to the minus beta out here. So here I don't need a dot dot dot. Okay, remember I wrote down a fundamental equation which I boxed and I discussed a lot. If you think of it for 4-point correlators, it's just this. Okay, I'm going to show you how it's satisfied with this definition. It's kind of clear, but let me just show you anyway. So think of the state psi, and state psi. How does O tilde omega 3 act on O omega 4 psi? Now, if you just think of this product of operators, this chain of operators, psi, use my rules one by one to simplify it. First, O omega tilde omega 3 goes to the right of O omega 4 and gives you a factor of e to the minus beta omega 2, minus beta omega 3, right? So you get this is equal to O omega 1, O tilde omega 2, O omega 4, O omega 3 adjoint into psi. This is true from the rule I wrote for O tilde omega 3, right? Now I have O tilde omega 2, but I can use the same recursively so as to get e to the minus beta into omega 2 plus omega 3 by 2, right, into O omega 1 into O omega 4. But now because O omega 2 appeared second, it's also going to commute through this, because now this whole thing is 1 A alpha. Omega 4 and omega 3 together give me one polynomial. So O tilde omega to the right of this entire polynomial by the linear equations I wrote down. And so you'll get omega 1, omega 4 into O omega 3 dagger into O omega 2 dagger on psi. Okay. Now I just sandwich it on the left with psi, and you see that the equation is satisfied. Okay. So these O tilde omega operators, these mirror operators, have done the magic that we wanted them to do. That they've moved to the right, they've given you the e to the minus beta factors, okay, and they've reversed their relative ordering. Okay. There was a second condition for things to be smooth, which was just that these correlators of these operators should look like thermal correlators. Okay, this was at psi of A alpha psi, where A alpha is just a product of ordinary operators, should look like trace of e to the minus beta h into A alpha. This is just a condition about the thermal nature of a generic state. So if you have a generic state and you think of ordinary operators and you try and consider the expectation value of an ordinary operator in a generic equilibrium state, at least I'll talk about non-equilibrium states later, that's the same as a thermal average. That's just some general issue about eigenstate thermalization and equivalence of ensembles. Okay. So that second condition is just met automatically. Once you've reduced it to this form, then you can use in addition this condition, which is a generic condition, to also convert this, this product into a thermal trace. Okay. So these operators O omega that I wrote down are meeting the fundamental conditions we had for getting a smooth horizon. So this means that since you can define these operators O omega and O tilde and we prove their existence, this is in some sense a statement that in AdS CFT you can obtain a smooth horizon. Okay, by constructing these local operators, by computing the 2-point function across the boundary, I'm constructing for you operators that satisfy all the right properties of local fields, and they have a smooth 2-point function across the horizon, and so this indicates there's no firewall. Okay, so this is evidence for the absence of a firewall, the existence of these operators O tilde. Now you'll ask me, well, but Mathur and AMPS gave you several arguments why these operators O tilde don't exist. So how is it that you're able to get around these arguments? Let me show you, how to get around these arguments. Okay. The first argument of mass MPS is what's called, so I said it in some order, let me discuss it in this order today. So first there's what's called strong subadditivity. The solution to the strong subadditivity paradox, which comes out in a very natural and precise form by these O omega constructions, is that C equal to inside, okay, is actually a subset of A equal to outside. So these are the outside degrees of freedom. Okay. So this is the condition, this is the solution which I'll now try and justify from this construction. Yeah. This comment, this is just a comment about generic states. In generic states, the expectation value is a thermal expectation value. Because I wrote down this equation yesterday about what was the condition for a smooth horizon, which was just this. A, you get this, and B, you should be able to convert this to a trace. Okay, yeah. It was only important in that I wanted to discretize the set of operators I had. I said the linear equations have a solution because I had a discrete set of operators for which I wanted the linear equations to work. Okay. Okay. Now this is the solution. Okay. In some sense, this is what's also called complementarity, but it's a precise version of black hole complementarity. How do we see this in this prescription? You see this as follows. You know, the way you see this is by the following statement, which may seem slightly surprising, but is true. If you think of O tilde omega and O omega prime, the commutator, okay, this is not equal to 0. As an operator, it's not equal to 0. Okay. How do I know it's not equal to 0? The way I know it's not equal to 0 is that if you think of the subset of states generated by all possible polynomials in the O's, okay, all possible polynomials, not polynomials with a restriction that I have. Okay. It's easy to show by counting that this overcounts in fact the number of states that you have in the CFT. So if you look at all possible O's, enough to generate all possible states that you have in the CFT. Okay, if you look at all possible Fourier operators of these O's. Okay. So I'm saying that if you look at all polynomials in the O's, then the number of all polynomials in the O's in fact is larger than the number of states in the CFT. So all polynomials in the O's in some sense, acting on some state, say even the vacuum state, give you an overcomplete basis for all states in the CFT. Okay. As a result, no operator O tilde omega that commutes with all O's, with all the modes of O omega. This is in, you can, yes, so that's right. There are relations amongst the O's that tell you there's some OP relations, but in the end, the point is that there is no operator O tilde omega that commutes with all the modes of the CFT. Okay. This is simply the argument, in another way of thinking of this, think of an evaporating black hole, you allow it to evaporate, you go after the page time. The modes outside, the degrees of freedom outside are in some sense, already capturing most of the Hilbert space. Okay. So in fact, there is no additional degree of freedom that commutes with all of them. Okay. So there is no additional degree of freedom that commutes with all of them. And in fact, if you tried to impose that this is 0 as an operator relation, you would find that you'd get an inconsistent set of linear equations. Okay. And I can show you also in some examples, this commutator is non-zero. Okay. So this is the statement that O omega tilde is in some sense a scrambled version of the O omega operators. It's living in the same degrees of freedom. It doesn't exactly commute with them. Okay. So it's living inside the same degrees of freedom, and but it's some scrambled version of those degrees of freedom. Okay. But there's something which is very important. And what's very important is the following. You don't want locality. I said O omega tilde and O omega are non-zero, but and think of one space like one Kruskal slice, okay? And you have one point here x1 and you have another point here x2. There's some O tilde degrees of freedom living here. There's some O degrees of freedom living here. It better be the case that the field here commutes with the field here, at least to an excellent approximation. Okay, if I just say that the inside is a version of the outside, that's okay. It resolves the strong subadditivity paradox. It resolves the strong subadditivity paradox because that strong subadditivity paradox holds for 3 independent Hilbert spaces. So it resolves the strong subadditivity paradox, but it looks like it's violating locality. If this commutator is not 0, then you would measure some field here, some field here on a space-like slice, and they'd fail to commute. So you'd have a violation of effective field theory. However, we've been clever in taking care of that because we've ensured that while this commutator is not equal to 0, it's equal to 0 on almost all states. I can write as dot equal to 0. And what this means is that within any correlation function, if you think of any correlation function with some number of insertions and then you insert this correlator and then you put some more insertions, so let me call this omega omega prime, omega 3, omega 4, whatever, up to psi, this correlator is 0 because the commutator annihilates the state and all vectors produced by acting on the state with a finite number of holes. Okay? So this commutator is effectively 0. It's non-zero, but it's non-zero in a non-observable sense, or it's non-zero in only when you measure n squared point correlators. So if you have a super observer on the CFT who can measure an n squared point correlator, then he sees the absence of locality between the outside and the inside, and it's not surprising. Okay? If black hole complementarity exists, a super observer in the CFT should be able to see it. So he sees the non-zero commutator only if you increase the number of insertions beyond n square or up to n square, or you do something else, you insert energy n squared in the CFT. Okay? So the commutator is effectively 0, but it's not 0 as an operator.
Because of that identity you wrote down.
This is because of the identity I wrote down. I can show you again, but let me show you here again. So let me this guy. Let me think of O omega tilde, one relation. O omega 4 on psi. Okay, this is the same as O omega 3, O omega 4 into O omega dagger on psi within e to the minus beta omega by 2. Okay, but what's the other side of this commutator? That's when O omega tilde appears to the first. But in that case also it goes all the way to the right. See, O omega tilde on O omega, that's the definition, right? This is still some operator acting. So this is also equal to O omega 3, O omega 3, O omega 4, O omega dagger acting on psi with e to the minus beta w. So this is also a polynomial. Where does it break down? It breaks down if you have so many insertions up front that you cross the edge of that A phi. Okay, so it does break down. It's not, but for all states and states produced by a finite number of excitations, which is really what you want to consider. You want to consider the black hole and probes of the black hole. You don't want to consider black hole and when you put n square energy, then all sorts of things happen. Okay, so that's why this commutator is the result of these two equations. Okay, yeah.
This is non-zero when you have say n square number of
Right.
insertions. But then so how does it resolve the paradox? I still don't.
So the operator is non-zero. This is non-zero as an operator. It means O omega tilde and the Hilbert space that spans A, which is made of O omegas, are really living in the same Hilbert space. So they're living in the same Hilbert space. So C and A are not independent Hilbert spaces. Then strong subadditivity doesn't apply. No, to apply strong subadditivity, you want two operator relations to be different. Now, strong subadditivity tells you have two Hilbert spaces which are independent, and then you apply the strong subadditivity.
So this is non-zero. Non-zero in 1 over 8 or something like that.
No, it's non-zero. It's not. No. That's not the right way to think about it. It's non-zero when inserted inside a very high point correlator. See, Sandeep is getting late. yeah. Huh. It's what? It's also on the vacuum. O omega tildes are not defined. O omega tildes are state-dependent operators. They're defined on psi.
You can't say it like that. I mean, you said yourself that the omega tilde, all the polynomials of omega are spanning the whole set of this thing. So, and if you can write omega tilde in terms of that, you presumably can write it. That's the way you were saying it, that you can.
But it's some state-dependent definition. It depends. It's a definition that depends on the state psi. You could take O omega tilde as defined on some state psi, and then you could say, let me act it on the vacuum, and it's non-zero. But what's the physical interpretation of that? Okay, can we discuss this issue later of how omega is defined outside the state at psi? If for a minute, if we restrict ourselves to correlation functions which have really the state psi that I started with and some correlators above that state. I'm very happy to discuss that, but if you can discuss it in the discussion, yeah, okay. Then I'll be happier. Okay, okay, great. So now let me describe the other things. I'm not saying I have an answer to that. I think it's something which deserves a lot of, I'm not saying I have a sharp answer to that. I just think for the questions right now, it's not. Okay, good. Now this is a resolution to the additivity paradox. Okay, what about the lack of a left inverse paradox? How do you resolve that? The answer actually, maybe it's Rajesh that asked me the question. The lack of a left inverse paradox is resolved in the following way. If you think of O omega tilde dagger on O omega, or you think of O omega and O omega tilde dagger, acting on the state psi, okay, you can check that this is in fact just, O omega tilde into O omega, sorry, let me just write this out. This is O omega tilde into O omega tilde dagger minus O omega tilde dagger omega tilde acting on psi. I did nothing, I just expanded out the. Now I'll use these rules that I had. So first O omega goes and turns into an O omega dagger, okay, and then this goes, so you can see that this is just the same as O omega dagger into sorry, it's the same as O omega dagger minus O omega dagger into O omega acting on psi. Okay, with no e to the minus beta factors. And the way this happens is, remember first the O tilde omega goes and acts on psi and turns into an O omega dagger. Okay? Then the O tilde omega dagger but goes to the right of that and turns into an ordinary O omega. That's how you get an O omega dagger and O omega. In one case you get an e to the minus beta w, in the other case you get an e to the plus beta w. So all those factors cancel. So you're left back with this ordinary commutation, which is just g omega on psi. This is what we call g omega. However, it's once again true that, if you think of this commutation relation, if you think of this commutation relation of omega with O omega dagger equal to g omega inside correlation functions or acting on psi and on descendants of psi. It's g omega as an operator. In particular, if you normalize them by root g omega, this is, but only inside correlation functions. It's not equal to 1 as an operator. So O omega dagger does not need to have a left inverse because the right hand side is not 1. And in fact, what the counting argument is showing you is that the right hand side has to annihilate some states. But which states it annihilates are outside this set of observables. So it annihilates some states that are very far from the original black hole that you started with. And that's fine. All we want is the creation and annihilation operators inside should effectively look like creation and annihilation operators in the field. So whenever I write dot equal to, this just means effectively, and effectively in a very precise sense, in that within the state psi and on descendants of the state psi. So these are creation and annihilation operators that act effectively exactly like creation and annihilation operators of a real field. But if you look at them very closely, inside some, if I replace this dot equal to by a c, by some commutator c, okay, then what I'm saying here is that there are some null vectors of c. What the counting argument AMPSS shows you is that there exists v such that v is equal to 0. So this commutator is not really 1, it has some null vectors. This is the extent of what the AMPSS counting argument shows you. Okay? And what I am showing you is that v does not belong to H psi. It's not in the state of the black hole and some excitations of the black hole by finite energy excitations. Okay? So this is the claim I'm making, and the AMPSS proof shows you this. Okay? So this commutator is effectively 1, but it's not really 1. Okay? And that's why this operator doesn't have a left inverse as a result, which is fine. It doesn't have a left inverse. Okay? But that's okay, because you only want it effectively to behave like a creation annihilation operator. Can I just complete one thing and then you can ask me all the questions in one go? Okay, ask me, yeah, go ahead.
So the point last time you were making that in CFT it grows with the energy,
Yes,
right?
yes.
So you are saying, suppose I have 10 states and lowered 4 states. So only 4 states will belong to my psi.
It's not 4 states. CFT states don't work like 10 and 4. CFT states are actually infinite. the dimension of a space is 10 and the dimension of the space is 9. Okay. If you think of how many of those states can be obtained by acting with a finite number of excitations on some state psi, you will see you can't get all the states. You in fact get a much smaller set of states. Okay. And so, you know, I can try and explain in more detail, but you know, the statement is just that the fact that there are lower states at lower energy and the fact that O omega dagger lowers the energy tells you there must exist some vector v, so that C on V is 0. This commutator has to annihilate some vectors. Okay, or O till, you know, O omega dagger has a null space, and that's okay. Let it have a null space. It has a null space, but this null space, whatever these null vectors are, don't belong to this H psi. They can be of same energy, but they're very far from the original black hole. Now it's true that O omega dagger is going to annihilate some states, but they're going to be, you know, some states which are very far away from the black hole. So there are some states in the same energy space or, you know, similar energy subspace of the Hilbert space, okay, which are annihilated by O omega dagger, but they are not anywhere close to your black hole, you know, close to your generic state that you started with. It could be. I don't think it's well. Yeah, I don't know how one defines microstate of the same. Yeah, so they do live in the same energy in some sense. There are some states of that energy which are indeed. Yes. Yes, and if you go to that microstate, though, the O tilde operators that you should use effectively are different. There's some, you know, they're state dependent operators. So they're defined in a state and some locality of the state. If you go to some far away microstate, then you have to use some different O tilde operators. So these are some state dependent operators, and so they have this property. Okay. The last thing which is important in the state dependent discussion, how do you resolve? Yeah, 2 minutes. What, are we at 4:13 right now? 4:43. Oh, sorry. Okay. 2 minutes and then I'm done. Just one last thing. Okay. Sorry. Yeah. Sorry. Just one last thing and then I'm done. Okay. I just want to explain how you resolve the. Okay. So how do you resolve this n alpha not equal to 0 paradox? Okay. I'm sorry. Going over time, not entirely. Okay. How do you resolve this? The first thing is that, you know, it's clear that n alpha is equal to 0. And the reason n alpha is clearly equal to 0 is because, you know, you can calculate n alpha. Okay? So remember, this n alpha was just one of the terms it had, okay, was some creation operator e to the minus beta omega by 2 a omega dagger. Okay? So it's clear that, and there's some creation operator, the adjoint of this operator. So it's clear, first of all, that n alpha on psi is 0. Okay, so the number operator as measured by the infalling observer is 0. That's clear. Okay. Now, how does it, you know, what's wrong with the argument of Marolf and Polchinski? Okay. Just to show you what's wrong, let me give you another example which also involves state dependent operators, and you'll see how the argument of Marolf and Polchinski fails for these kinds of state dependent operators, but the effective operator you're using depends on the state. Okay, think of the entanglement entropy that we have discussed a lot. Okay, so think of a Hilbert space which is a product of two spaces HA cross HB. Okay, so there is a Hilbert space which is HA cross SB, and you know, Tadashi taught us how to compute the entanglement entropy, okay, which is minus, okay, trace of rho A log rho A. Okay, so let me take let's say I want to compute this. So I take a state psi and compute SA equal to trace of rho A log rho A. Okay. Now let me use this argument that Marolf and Polchinski had. Let me go to a product basis. There's a basis of states for HA cross HB in which I can compute this trace. Okay. Go to a product basis. Okay, which is just VA cross VB. Okay, and there are, you know, VAI cross VBJ. Okay, there are many such states in the basis. There are as many vectors here and some number of here. Okay? And let me compute this trace in the product basis. Okay, in every vector of the product basis. Okay, so this is my product basis. It's Vij. Okay, and if I compute sum over Ij, Vij of, you know, rho A log rho A. Okay, there's an obvious fallacy here. This is clearly 0. Okay, because in every element of this product basis, okay, this density matrix has 0 entanglement entropy, because rho A log rho A is 0 if you're in a product state. Okay? So, trace of rho A log. Okay? So you see that in this product, if you go to this product basis to compute the trace, compute the entanglement entropy, you have hence proved that it's always 0. Okay? Now clearly this is fallacious, and the reason it's fallacious is because when you compute this, this is some state dependent operator. This rho A, this density matrix, is a state dependent operator. So what you mean by this trace is that you take the operator psi, you compute rho A for this vector psi. This is rho A for the vector psi, and once you have that operator rho A log rho A, then you take the trace on the Hilbert space. Okay? You can't make this change of basis for this state dependent operator, because if you make the change of basis, you will come up with this absurd conclusion that the entanglement is always 0. Okay? So the operators that we have here are exactly these kinds of state dependent operators, and so it's not permissible to make this change of basis between states that are generic states and states that are number eigenstates of the external operator, because the number eigenstates are indeed firewall states. Okay, so that resolves the last of the AMPS objections. Okay, so just to summarize, today I wanted to say a little more, but what I said today is that you can construct these operators O tilde, and based on our discussion in the past lectures, these operators O tilde and the construction of local operators, you compute 2-point functions across the horizon and say that they're smooth. Okay, and these operators O tilde resolve every one of the Mathur and AMPS objections, and they resolve them in the ways that I described. Now they resolve the strong subadditivity paradox through complementarity. They resolve this issue of commutators because they're designed to have unobservable commutators basically. They resolve the lack of a left inverse paradox because they only effectively obey the algebra of creation and hylation operators, not as operator relations. And they solve this n alpha not equal to 0 paradox because for such state dependent operators you can't make a change of basis. Okay, so that's how these operators resolve all these paradoxes, and then we can discuss more in the discussion session because I've already gone over time.
Urgent question which can't wait 15 minutes, ask it. Sorry. If there's a really clarification which you need urgently, do ask it because, it will be helpful. Okay, but if not, I won't press them to it. Let's thank